Hello everyone. Today we are going to see the third lecture of this course. The third lecture is on synthesis of nanomaterials by physical and chemical methods. So in this lecture we are going to learn how to synthesize nanomaterials by physical methods and chemical methods, and we are also going to learn what is nucleation and growth and how to synthesize metal nanoparticles and metal nanorods. And we are also going to see a small simple experiment to understand how we can synthesize cellular nanoparticles in a lab with the available chemicals. So let us see physical methods. Under the physical methods there are several types are available, but in this lecture we are going to mainly focus on mechanical milling and laser ablation. So let us first see what is mechanical milling. So it is a top down process. You know what is top down process? It means you are making from bulk to nanomaterials, and here the nanoparticles formed in a mechanical device is generally referred to as a mill. So here we are going to use a metallic ball, so that is going to break your bulk material into nano size particle. Let us see the principle of milling. So the fundamental principle of size reduction in the mechanical device is the energy imparted to the sample during impacts between the milling media. So this model represents the moment of collision. Here you can see here the particles are trapped between the two colliding balls within the space occupied by the mass of powder particles. So this animation will tell you how the mechanical milling works. So here you can see here the metallic balls are rotating, so the metallic drum is rotating and the metallic balls are falling on that powder, and it is going to break the micro size powder into nano size particles. So this is a mechanical milling or ball milling equipments. We can also call it like a ball milling because we are using metallic balls, and this is an electron microscope picture. So as I told you earlier, for seeing these nanoparticles you need a electron microscope. So this is a scanning electron microscope picture. You can see here figure A is after 3 hours of milling, and figure B is after 9 hours of milling, and C is 15 hours and D is 20 hours. So you can see here with respect to time the particle size is going down, and whenever you take the picture you have to insert the scale bar. So the scale bar is very important, it will be useful for calculating you the size of the particles. So let us see the next method, that is laser ablation. Here you will be using the laser light to vaporize your material, and the nanoparticles by laser ablation, which involves the generation of nanoparticles by a laser ablating of a solid target. Okay. So we can get the nanoparticle in the gaseous, or it can be obtained from the liquid environment also. So it depends on the environment, you can get the particles in the nanopowder form, or it can be in a colloidal solution form, and it is one of the easiest and fast method. And here when you compare to the other methods, it do not have any long reaction times, and it do not have any multiple steps, and it does not require any toxic chemicals for its synthesis. So it is also called as environmental friendly or green method. So in this method the resulting nanoparticles which we are obtaining in the colloidal solutions are ultra pure. So these particles do not contain any counter ions or any reaction byproducts. So we can use that particle as such for the biological applications, and again we can also add ligand to these particles. We can add the ligand after the synthesis process, or we can add the ligand in the suitable solvent itself, so it can be coated on the surface of the nanoparticles. How to synthesize these nanoparticles by laser ablation? If you want to synthesize silver nanoparticles by laser ablation, you need a high purity silver slice, and if you want to make the copper nanoparticles, you need a high purity copper slice at the bottom of the glass vessel containing 20 ml of water. And if you apply the laser light like 1064 nanometer pulsed ND-YAG laser and operating a fixed energy of 30 minutes, so this will result in yellow color in case of silver nanoparticle, and it will appear light green in the case of copper nanoparticles. So this is the experimental setup of laser ablation. You can see here. So the synthesis of nanoparticles by laser ablation liquids, it is one of the simplest experimental configuration, and here you are going to keep your metal slice. If you want to make the silver nanoparticle, you are going to keep the silver slice, and if you want to make the copper, you can keep the copper slice in that here. And when you apply the laser light, it will vaporize the material, and the nanoparticle can be obtained in the colloidal solution form. And here we can use that x, y, z stage to move the target, and you can utilize the complete material for making the nanoparticles. So, this animation will give you a clear idea how the laser ablation works. You can see here this YAG laser is applied to the metal target. For example, if you want to make the silver nanoparticle, you will be keeping this silver metal here, and if you want to make the copper nanoparticle, you will be keeping the copper metal here. So, when you apply this laser light, it will vaporize the metal and this nanoparticle will be collected in the aqueous media, and using this XY stage you can move this target to the XY and Z direction. So, you understood how we can make nanoparticles by physical methods using mechanical milling as well as laser ablation. So, now we will see how we can make nanoparticles by chemical method. For synthesizing nanoparticle by chemical method, we need three important components. First one is metal salt, and second one is reducing agent, and third one is capping agent. So, these are some of the examples for reducing agent: sodium citrate, sodium borohydride and ascorbic acid, and these are some of the examples of capping agents: thiols, citrate and polymers like polyvinyl alcohol and PVP. Okay. So, what happens here is, so this reducing agent will reduce your metal salt into metal nanoparticle, but these metal nanoparticles are highly unstable, so it will try to join together and form the agglomeration or aggregation. So, to make the nanoparticle stable, we have to add a capping agent or stabilizing agent that will prevent the aggregation or agglomeration. So, synthesis of any nanomaterials involves two important steps. One is nucleation, another one is growth. So, what is nucleation? So, nucleation is the phenomenon of initiation of formation of first nanocrystal in the solution. So, it involves the appearance of very small particles or nuclei of the new phase which are capable of growing. So, for biological cell, how nucleus is important? Similarly, for nanoparticle, this nuclei is very important. There are two types of nucleation. First one is homogeneous nuclei, it forms simultaneously and uniformly throughout the solution, and next one is heterogeneous nuclei. So, it nucleated at different time point. So, let us see here, this picture is Lam's diagram at versus time versus solid concentration. So, once the nucleus is formed, then the growth will start. So, if the nucleation is homogeneous nucleation, that means all the nuclei form simultaneously, you will get monodispersed particle. Monodispersed means uniform size particle, and if the nucleus is heterogeneous, that means it is nucleated at different time, that means it is polydispersed particle, that means you do not get the uniform size particles. So, when you see that nanoparticles under transmission electron microscope, you can see here uniform size particles, that is called as monodispersed particles, and it is ununiform size, that is polydispersed nanoparticles. So, this nucleation play a very important role in controlling the properties of final product like size distribution as well as the nature of the phase. For making a very small size nanoparticles, you need a strong nucleation and slow growth. So, you can get a highly uniform size particles if the process of nucleation and growth can be successfully separated. So, this is the typical precipitation reaction. So, here we are going to use a metal salt and reducing agent. So, this reducing agent is going to reduce your metal salt into metal atoms. These metal atoms combine and form the clusters. These clusters combine and form the crystal size. So, this crystallite will combine and form the primary particles. This is the nucleation step and this is the growth step. So, these primary particles combine and start growing. So, we have to stop the growth, otherwise what happens is all the particles combine and grow like a very big size particle, that is agglomerated particle, which is not useful. We need a small size particles for our applications. So, how we can achieve that? By arrested precipitation method. What is arrested precipitation? Here a large number of nucleation centers are formed by vigorous mixing of the reactant solution. So, when you make your nanoparticle, we have to mix it vigorously. When you mix it vigorously, you will have more number of nucleation. So, this I will show you in the last with a simple experiment how to make this and how to mix it vigorously. And here if you keep the concentration growth kept small, the nuclear growth will be stopped due to lack of material. So, this is called as arrested precipitation, and we have to stop the particles from the Ostwald ripening. So, how we can stop the Ostwald ripening? By using the stabilizer. What is Ostwald ripening? The growth mechanism where small particles dissolve and are consumed by the larger particles. What happens is, as a result of this, average nanoparticle size get increased with time. So, and the particle concentration get decreased. So, if the particle size is increased, it decreases the solubility. So, this is called as Ostwald ripening. That means the small particle dissolve and consumed by the larger particles. By using the stabilizing agent, we can protect it from the Ostwald ripening. We can protect the particle from the Ostwald ripening. So how we can tune the size of particle? The tuning of the size of particles can be achieved by controlling the nucleation as well as the growth rate. For example, fast nucleation will provide high concentration of nuclei and it will yield a smaller nanocrystals, but when you use the slow nucleation, it provides a low concentration of seeds and again the same concentration of precursors. So that results in the larger particles. So a simple example is, if you have a 5 person and if you have 50 rupees, each will get 10 rupees. But again, if you have the 2 persons, they each can share like 24 rupees each. So similarly, here you can see here, if you have the more number of nuclei and the precursor amount is same. So what happens is, you will get a small size particle, and during the slow nucleation, you are having only 2 nucleus, but again the precursor is same. So everything, all the unit is consumed and the crystal size is bigger, it is growing bigger size. And what is the role of stabilizing agent? It is preventing the uncontrolled growth of particles, and it will prevent the particle aggregation, and it will control the growth rate, and also it will control the particle size, and it will allow the particle solubility in various solvent also. Let us see how the stabilizing agent works. There are 2 types of stabilization, one is electrostatic stabilization and the other one is steric stabilization. So what is electrostatic stabilization? It means adsorption of ions to the surface. So it creates an electrical double layer, so which results in a Coulombic repulsion force between the individual particles. So the uniform particles charge, it will repel each other, so it will give a electrostatic stabilization. The next one is steric stabilization, that means the metal is covered by a layer of material that are sterically bulky. Okay. So for example, polymers and surfactants could be used, so that is example for the steric stabilization. So these are the parameters which is going to affect the particle growth, shape and structure. So what kind of capping agent we are going to use, what is the reducing agent, whether you are going to use a strong reducing agent or weak reducing agent, and what is the concentration of reactants, and again the pH of the solution also important, and duration of heat treatment. In some cases the heat treatment is going to favor the fast nucleation. So this is a typical picture of your metal nanoparticle synthesis. You can see here, if you want to make gold nanoparticle, you can use the gold metal precursor, and we are going to reduce using the reducing agent. So that is going to reduce your metal salt into metal nanoparticle. Let us see how we can synthesize gold colloids. For synthesizing gold colloid in water, we have to use this metal precursor, hydrogen tetrachloroaurate, and a solution of trisodium citrate. It is your reducing agent. So here we can get the gold nanoparticle in the size of 10 to 20 nanometer, and again in this reaction the citrate act like a weak reducing agent, and also it act like a stabilizer. Okay. So a layer of citrate anions adsorb around each nanoparticle, and it prevents from the aggregating, because the citrate ions give the uniform charge to the nanoparticle. By electrostatic repulsion it will be separated out. So here the citrate act like a reducing agent as well as it also act like a stabilizing agent. So at the finally you will get the ruby red color. When you get the ruby red color, you can confirm you got the gold nanoparticle. So why this metal nanoparticle showing different kind of colors? You can see here different size and different shapes showing different kind of colors. This is a silver, and it is showing different kind of colors with respect to size and shape, and again this is a gold spheres of different size, and this is a gold nanorods, and it is also showing different colors. So what is the reason for these colors? The reason is the surface plasmon resonance. The metal nanoparticles will show surface plasmon resonance. That means the incident light creates oscillation in the conduction electrons of the surface of the nanoparticles, and the electron magnetic radiation is observed. So let us see what is surface plasmon resonance. So when the nanoparticle is much smaller than the wavelength of light, the coherent oscillation of the conduction electron bands induced by the interaction with the electromagnetic field. So this resonance is called as surface plasmon resonance, and these are the factors which is going to control the size or shape of the nanoparticle. So you can see here the concentration of your reducing agent, that is going to control the size of the particles, and also the stirring rate, and again you have to use the fresh solution, filtered solution always to make the nanoparticles, and again stabilizing agent, one kind of stabilizing agent you are going to use, that is going to decide the size and shape of your nanoparticles. So let us see how to synthesize gold nanorods. Okay. So it is a two-step process, like you can see here. it is a seed mediator growth for gold and silver. Here we will be using this gold or silver salt. If you want to make a silver nanorods, you have to use the silver salt, and if you want to use the if you want to make gold nanorods, you have to use the gold as a metal salt. And we are going to use the NaBH4, that is sodium borohydride. It is a very good strong reducing agent. What happens is, when you use that sodium borohydride, it will reduce this gold into very small size particle, and you will get the seed formation. Okay, and here citrate will act like a capping agent, stabilizing agent, and it will inhibit the particle growth. So you will get the seed, and this next step you will use the seed, then you will add the gold or silver salt, and you will add the weak reducing agent, that is ascorbic acid. When you add the weak reducing agent, what happens is, here it will favors the growth. Okay, and here you are using a different kind of stabilizer, that is C-tap. So this C-tap stabilizer, it will provide a rod like template, so you will get a rod shape. Nanorods you will get in this step. Okay. So when you use that strong reducing agent, you will get the seeds, and when you use the weak reducing agent, you get the nanorods. Okay, and also we have to use the stabilizer. This C-tap stabilizer plays a major role in formation of nanorods. So this is a synthesis of gold nanorods. So here you can see here, in the first step we are going to use that gold solution and sodium citrate, and we are going to mix with the sodium borohydride, and you will get a nanoparticle of 4 nanometer diameter. So this is your seed. And second step is stock solution. Here you are going to use the gold solution plus you are adding the C-tap stabilizer, and you are going to add the ascorbic acid. So when you add the ascorbic acid, what happens is, it is reducing the gold Au3 plus to Au1 plus. It results in the disappearance of color, and it is a 3-step protocol for nanorod synthesis. So first step is, like, you take a 1 ml of seed and mix with 9 ml of your stock solution, and from here you take 1 ml and mix 9 ml of your stock solution, and from here you take the 10 ml plus 90 ml of the stock solution. Finally you will get the nanorods. So this nanorods size synthesis depends on the seed size as well as the length of tiles, that is by the C-tap. Okay. So if we have the more C-tap and other things, it is going to play a major role in the nanorod size and dimension. So what is the growth mechanism of gold nanorods? The first step is nucleation, followed by that you will have the growth, and followed by that you will have the development of facets. So once the facets is formed, what happens is, this C-tap stabilizer will go and bind to this facet, and it will continue to grow in until all the reagents are exhausted. So this C-tap, it is a positively charged bilayer, and it stabilizes the nanorods, and based on this idea we can make a several size and shape of gold nanoparticles. Only thing is, you are going to change the concentration of reducing agent and concentration of stabilizing agent. By just playing around with this concentration, you can get a different kind of shapes like cubes, hexagon, triangle, and you can have a different kind of shapes. So here you can see a simple example. So we are going to use this ascorbic acid, and we are going to increase in the concentration of ascorbic acid from A to C. So when you increase in the concentration from A to C, and we are increasing the seed concentration from C to D. So when you play around this with the ascorbic acid, that is reducing agent as well as the seed concentration, we will get a different kind of shapes and different kind of size. So this tabular column will give you a clear idea. So if you use this concentration of C-tap, and if you use this concentration of Au seed, and this concentration of Au3 plus, and this concentration of ascorbic acid, you will get this kind of different shapes. So we are going to use these 4 components, and we are going to achieve different kind of shapes and different size. Only by changing the concentration of these 4 components, we are achieving different size and different shape. So if I ask you to select a nanoparticle based on size for a catalytic reaction, which one you will select? So we will select, yes, you are right, we will select the smallest size. So if I ask you to select nanoparticle from this tabular column for catalytic activation based on the size, we have to select the smallest size, because the smallest nanoparticle will have highest surface area to volume ratio, it will have more catalytic activity. So, let us see how to synthesize silver nanoparticles. Okay. So, here we can use this silver nitrate AgNO3 and your sodium borohydrate. This is a reducing agent, and this reducing agent will act like a also stabilizer. You can see here. So, from Ag plus it became Ag0, and this borohydrate protecting these nanoparticles from aggregation or agglomeration. So, in silver nanoparticle you will get yellow color. You can see here these are silver nanoparticle, but these are of different size. Okay. So, you can see here the silver colloids of if you see this is a, if we have a yellow color, pale yellow, that is like we have a very small size particle, and if we have this kind of color, that means the particles are aggregated, it is not useful for the further applications. And how do you control and how do you stabilize this nanoparticle? You can see here the ratio between your metal salt and reducing agent is very, very important. If the ratio is 2, it is highly stable. If the ratio is 2.1, it is stable for 30 minutes, and if the ratio is 1.9, it is stable for only 20 minutes, and if the ratio is 1.8, it is stable only for 5 minutes. Okay. So, when you optimize any synthesis protocol, you have to think and you have to optimize. Okay. So, this is very, very important for making a very good stable nanoparticles. So, when you made the nanoparticle, the first step of your characterization is you will be using this UV visible spectroscopy. I guess most of them know what is UV visible spectroscopy, and most of the lab you will be having this UV visible spectroscopy. So, what you have to do is you have to transfer this 1 ml of solution to a quartz cuvette. Okay. So, you take it to the cuvette and you will do the scanning of this solution. So, when you start the scanning from 200 to 800, so you will get the lambda max at 400 wavelength. Usually the silver nanoparticles gives the lambda max at 400 nanometer range. Okay. So, if you get this kind of peak, you are sure that you got silver nanoparticle. So, from the silver nanoparticle peak, you can approximately calculate the size. For example, if you are getting the lambda max at 395, the particle size is approximately 10 to 14, and if you get the peak at 420, the size of the particle is 35 to 50, and if you get the peak at 438, the size of the particle is 60 to 80. And the next step is you have to take it for the transmission electron microscope. You want to see the particle. Okay. So, when you see under this electron microscope, you can see the particle size, and as I told you earlier, when you take any microscope picture, we have to include this scale bar. So, here you can see this scale bar is 20 nanometer. So, assume this scale bar is approximately 1 centimeter. Okay. And when you use this scale bar, so when you use this scale bar and move it to this particle, so you can see here this is like 0.5 centimeter. So, if it is 0.5 centimeter, you can calculate it is like 10 nanometer particle. So, based on this scale bar, we can easily estimate and calculate the particle size. So, let us see the nano rod formation. So, when you use the silver salt and if you make the nano rods, what happens is like it will give 2 peaks. When you see the nano rods under UV visible spectroscopy, it will give 2 peaks, and if you see this is the red color one is the seed. Okay. And remaining all are nano rods of different size nano rods. So, why it is giving 2 peaks? What is the reason? You can see here the nano particle is giving a single peak, but the nano rod is giving 2 peaks. So, what is the reason? The nano rod is giving 2 peaks because it has 2 dimension. So, it has dimension like this as well as like this, like longitudinal and transverse. So, it will give a 2 peaks, transverse as well as longitudinal peaks. Okay. So, let us see a simple experiment. I will demonstrate you how to make nanoparticles in your lab with simple chemicals available in your lab. Okay. So, for this we have to use 1 ml of deionized water in a 1.5 ml microcentrifuge tube, and we will be adding 1.67 microliter silver nitrate solution. Okay. That is of 0.1 molar to this above tube, and we will immediately add 1.33 microliter of freshly prepared 2 milligram per ml NaBH4 solution to it. Okay. So, the sodium borate should be a freshly prepared solution, and then you add 90 microliter of HA solution to this above solution. It is a stabilizer, it is going to stabilize your silver nanoparticle, and you have to mix it vigorously. Then if you see the yellow color, that means you are sure that the silver nanoparticle is formed. So, let us see the experiment. I will demonstrate you. So now we are going to see how to make cellular nanoparticle by using a simple experiment with the available chemicals in the lab. The first step is we have to take 1 ml of deionized water in a 1.5 ml tube. This is a 1.5 ml micro tube. So here I am going to take 1 ml of deionized water. So I am taking 1 ml of deionized water in 2 tubes, because to one tube I am going to add a reducing agent and the other tube I am not going to add reducing agent. So that you will get an idea, the tube which I add a reducing agent, it will reduce the silver salt into silver nanoparticle. The other tube which you do not have the reducing agent, it will be transparent, it will not form any nanoparticles. And from this I am going to remove 93 microliter of water, because in the subsequent step we are going to add 90 microliter of SDS and 1.67 of selenitrate solution and 1.33 of sodium borohydride solution. So the next step is I am going to add 1.67 microliter of silver nitrate solution. So this silver nitrate solution is light sensitive, so you have to use covered with aluminum foil, and always wear a gloves and also lab coat when you make silver nanoparticles. So I am adding this silver nitrate solution to both the tubes. So now I am going to add 1 ml of water to the sodium borohydride. As I told you earlier, the sodium borohydride should be prepared freshly. So what we did is we already measured 2 milligram per ml, that is we have measured 2 milligram in a 1.5 ml tube. To this I am going to add 1 ml of water and I am going to make sodium borohydride freshly. Just mix it so that the sodium borohydride can dissolve completely, and immediately you have to add the freshly prepared sodium borohydride 1.33 microliter to this tube. So I am going to add 1.33 microliter of sodium borohydride to only one of the tube, not to both the tubes. And I am adding immediately the SDS, 90 microliter of SDS to both the tubes. So now I am going to mix it vigorously both the tubes. So now we can observe the yellow color formation. That means the nanoparticle is formed. So you can see here the tube which I added reducing agent, it reduced the metal salt into silver nanoparticle. You can see here this has become yellow color. The other tube where I didn't add the reducing agent, it is transparent. That means the silver nanoparticle is formed in this solution where we added reducing agent. The other tube where there is no reducing agent, there is no formation of silver nanoparticle. Hope you understood the experiment, how we can make nanoparticles in the lab. And as a summary of this lecture, So, in this lecture we have learnt what is mechanical milling and what is laser ablation. So, these are two physical methods, and using the physical methods how to make these nanoparticles, and you learnt this mechanical milling is a top down approach, okay. And again this laser ablation is a green method and eco friendly method because we are not using any toxic chemicals. And we have also learnt how to make nanoparticles by chemical reduction method. For chemical reduction method you need three important components. What are those three important components? You need metal salt, reducing agent, as well as capping agent or stabilizing agent. And we have also learnt what is nucleation and what is growth. So, nucleation is formation of first nanocrystalline solution and followed by the growth. And we have also learnt how to make nanoparticles, metal nanoparticles and metal nanorods, and what is the mechanism of nanorod formation. And by simple experiment we also understood how to make nanoparticles in a lab with the available chemicals, okay. I will end my lecture here. Thank you all for listening. I will see you in another interesting lecture.